True or false? This figure represents a square number. That's false. A square number would be represented by a square array of dots, in this case 9. Draw the gnomons for this figure. True or false? The height to width ratio of the gnomons does not change. If you draw the gnomons and then look at the height to width ratio, you'll see that this is a false statement. The gnomons have ratios of 1 to 2, 2 to 3, and 3 to 4, and these are not equal ratios. True or false? The Pythagoreans would have considered this figure to be limited. If you draw the gnomons, you'll see that the answer is false, and that's because the ratios of the gnomons are not equal. True or false? Every gnomon in this figure contains an even number of points. This is true. If you draw the gnomons, you'll see that the smallest gnomon has 2 points, and the next one has 4 points, and the next one has 6 points, all of which are even numbers. True or false? The Pythagoreans considered even numbers to be feminine and odd numbers to be masculine. That's true. Find the common difference in the arithmetic progression. To find the common difference, you can find the difference between any two consecutive terms. For example, 21 minus 12 is 9. So that means to get from one term in the sequence to the next, we're adding 9 each time. Find the common ratio in the geometric progression. To find the common ratio, you can find the quotient of consecutive terms. For example, 12 divided by 3, which is 4. So that means to get from one term to the next term, we multiply times 4. Find the mean proportional, or geometric mean, of 9 and 16. The mean proportional is plus or minus 12. Find the arithmetic mean of 32 and 16. The arithmetic mean is 24. Find the harmonic mean of 5 and 9. The harmonic mean is 45/7. Through experimenting with plucked strings, the Pythagoreans discovered that the musical interval 1 to 2 was pleasing to people's ears. What was this interval called? It was called the octave. The Pythagoreans also discovered that the musical interval 2 to 3 was pleasing to people's ears. What was this interval called? This was called the perfect fifth. And the Pythagoreans discovered that the interval 3 to 4 was pleasing to people's ears. What was this interval called? It was called the perfect fourth. A monochord has a 36-inch long string. To what length should the string be shortened to produce a tone which is a perfect fourth higher than the tone produced by the original 36-inch string? So if we set up a proportion and solve, we'll find that the string should be 27 inches long. What number is associated with the sacred tetractys? That's the number 10. The sacred tetractys is the result of summing what four numbers? It's the numbers 1 plus 2 plus 3 plus 4. If you look at the triangular number 10 as a triangular array of dots, you can see that the first row contains 1 dot, the second contains 2, the third contains 3, and the fourth contains 4. Name geometric shapes that the Pythagoreans associated with 1, 2, 3, and 4. 1 was a point, 2 was a line, 3 was a plane, and 4 was a solid. Amy claims that 15 is the harmonic mean of 12 and 20. Which of the following would prove that her claim is correct? Amy needs to show that the reciprocals of 12, 15, and 20 form an arithmetic sequence. If she rewrites each of these fractions with a common denominator, she can see that they do form an arithmetic sequence because the common difference is -1/60. That means that the numbers 12, 15, and 20 do form a harmonic sequence. Which of the following is true about any two consecutive triangular numbers? It's true that any two consecutive triangular numbers will sum to a square number. For example, here's 3 square numbers. And we can see that each of the square numbers is the sum of 2 triangular numbers, 2 consecutive triangular numbers. So 4 is the sum of 1 and 3. 9 is a square number. It's the sum of 3 and 6, which are both triangular numbers. And 16 is a square number, and it's the sum of 6 and 10, which are both triangular numbers. The floor plan for a house shows that the library has a length-to-width ratio of 3 to 10. If the builder wants the library to have a length of 8 feet, what will be the width of the library? If we write ratios comparing the length to the width and then form a proportion, we can solve the problem. So 3 to 10 as a ratio must equal 8x, because 8 is a length and x is the unknown width. If we multiply and solve, we'll see that the width of the library needs to be 80/3 feet, or we could also call it 26 2/3 feet. To practice the constructions, draw the points and the lines that you're given to start with on paper and then do the constructions on your paper. Use a compass and straight edge to construct a perpendicular to line L through point P. So we're going to put the point of the compass on this point, and we'll make an arc to the left of that point, and without changing the size of the compass, we're going to make an arc to the right of that point. Next, I'm going to take the compass and stretch it out a little bit longer, because what I want to do is make two arcs that intersect either above or below this line segment. I'm going to make mine above. Now I've got these two intersections of these arcs and this line, so my point of the compass can go on those intersections. I'll put the point of the compass on this left intersection and make an arc above the line. And then without changing the size of the compass, I'll put a point on this intersection and make another arc above the line. That gives me two intersecting arcs, which really creates another point. And if I connect that point up with the point that's on the line, what I'll have is a line segment, or if I put arrows on the end to indicate that it goes on forever, it could be considered a line that is perpendicular to the original line, and it contains point P. Use a compass and straightedge to construct the arithmetic mean of the two given line segments. Now, if you keep in mind what an arithmetic mean is, it's basically an average. It will help you see how to do this construction. So to average two things, we add them together and divide by 2. So that's basically what we're going to do geometrically here. So the first thing I'm going to do is make a line segment that I think is more than the sum of the distances of these two line segments added together. So that looks a lot longer. Okay, next thing we're going to do is copy both of those line segments to this line segment. We've already seen that construction before. So I'm going to copy segment AB down to this line segment. Copy segment CD, so I'm measuring it, to the line segment as well. So this line segment is the same length as AB. This one is the length of CD. So if I go from this point, I'll call that E, to this point that I'll call F, segment EF has a length that's equal to the sum of the lengths of these two line segments. But I want to take this and basically divide it by 2. So that means I need to bisect that line segment. We've already seen that construction. I'll take the compass and stretch it out to more than half the distance between E and F. I'll make an arc above and an arc below, and without changing the compass setting, I will put the point of the compass on F, make an arc above and an arc below. And now I have two more intersections. I'm going to connect those intersections up, and I will have a line segment that intersects line segment EF. I'm going to call this point G. So segment GF, the length of segment GF would represent the arithmetic mean of the lengths of segment AB and the length of segment CD. Construct the golden sequence through phi to the third power on the line below. Segments measuring 1 unit and phi units are already shown. So what we're starting with is a line segment that has some points placed on it at some specific distances. So we're going to call the distance from A to B 1 unit, and we're going to call the distance from B to C phi units, because this distance from B to C is about 1.618 times the distance from A to B. If I want to construct a segment that is phi squared units long, what I'm going to remember is that phi squared is the same thing as 1 plus phi. So this distance measures, or this segment measures 1 unit, and then this one measures phi units. So to find the sum of those distances, I'll just take the point of my compass and put it on A, and put the pencil on C. So this distance is 1 plus phi, which I can now transfer over here. I'll call this point D. So this is 1 plus phi units, which means it's phi squared units long. Now I don't quite have enough room here to show you the whole thing, but if I wanted to make a segment that was phi cubed units long, I would have to sum phi and phi squared. So I would simply find this distance. That distance is phi cubed. Don't quite have enough room to put it over here and show you, but I could, if I had a long enough line segment, extend this, but this is still the distance. Use a compass and straight edge to construct the geometric mean of the two given line segments. Now this construction actually starts off exactly the same way that the last one did. We need to copy both of those segments to another line segment. So I'll draw a line segment that I know is longer than the sum of those two segments. I'll make a point on my line segment. I'll measure the distance from A to B and copy that distance to this line segment. I'll measure the distance from C to D and copy that distance as well. Now what I want to do is make a semicircle that has these 2 points, and let me just call this one P and I'll call this one Q. So I want to make a semicircle that has segment PQ as its diameter, which means I need to find the center of my semicircle. So I need to find the midpoint of PQ. Now we've done that before. I'm basically going to bisect this line segment. So I'll stretch the compass out so that it's more than half the distance from P to Q. I'll make an arc above and an arc below. And then I'll put the point of the compass on Q, make an arc above, and an arc, whoops, below. I need to make this one a little longer, don't I? That is easy to do. There we go. So now, if I connect up these 2 points, these 2 intersections, and I look to see where that crosses segment PQ, this point right here, I'll call that C for center, is going to be the center of my semicircle. Now if that's the center, then the distance from C to Q or C to P would be the radius of my semicircle. So I'm going to measure that distance about like that. And then I'm going to draw my semicircle. And hopefully I don't slip too much here. Like that. That's okay. I'll come back around here and try to draw from the other direction. Now you can probably see this is a little bit off here. Sometimes in your constructions you will be a little bit off because your compass will slip. That's okay. As long as all of the arcs are there that explain the story of the construction, you've still got a good construction. Alright, so the next thing I want to do is take a look down here at this original line segment. Now remember, from P to this point right here, which we didn't name, let's go ahead and give it a name. We'll call it E. From P to E was this same length as from A to B, and from E to Q was the same length from C to D. And what I need to do is construct a perpendicular to this original line segment that contains the point E. And that's also a construction that we have already done. So in order to do that, I need to put the point of the compass on E and find points on either side of E that are the same distance from E. So there's a point on the right side. I'll just turn the compass around. There's a point on the left side. Oops, make that arc a little bit bigger for you. There we go. All right, so then what I want to do is stretch the compass out longer. And I need to find a point up here that is the same distance from these 2 intersections we just drew. So here is one arc going from this arc that we just drew. And here is, without changing the size of the compass, second arc going from this intersection. Now that intersection, if I connect it up with point E, will give me a line segment that's perpendicular to the original line. So where is this arithmetic mean? Well, the arithmetic mean actually is this part of that line segment. So rather than connecting up this intersection all the way down to point E, I'm only going to go from where that line segment intersects the circle, and I'll call that F. So line segment EF, the distance, the measure of line segment EF, is the geometric mean of line segments AB and CD. Given that square ABDC measures 1 unit on each side, use a compass and straightedge to construct the golden ratio. Label the golden ratio phi in your construction. Alright, so here's our square. Now the first thing we want to do is find a length that is 1/2 of the length of the side of the square. In other words, we need to bisect one of the sides of our square. So I'm going to choose to bisect this side. That's a construction we've done before. So I'm going to stretch the compass a little more than half the distance across that side. I'm going to make an arc above and an arc below. And then without changing the setting on my compass, I'm going to make an arc above and below. I don't think you can see the arcs below. You're just going to have to trust me that they're there. And I'm going to use those two intersections to define the midpoint of that line segment. So now I know how long a side of the square is, and I also know how long half the side of the square is. Now the next thing I'm going to do is extend both the top and the bottom sides of this square. So I'm just going to use my straightedge and just extend this, and up here extend this side. Now we know that we still have parallels even though we've extended, because these two sides are parallel. Alright, so the next thing we want to do is use the compass to measure the distance from this intersection where we bisected the side of the square up to this corner of the square. And what we're going to do with that is make an arc, and notice the point of the compass is still down here at this intersection. Make an arc that intersects both of these extended line segments. So it's going to intersect this vertex and this extended line segment. Alright, now if you look at the distance from, and let me just label these so we know what we're talking about. Let me call this A, and let me call this B, and let me call this one C. Alright, so what we've got are basically 3 vertices of a rectangle. We simply need the 4th one up here. So what I'm going to do is take my compass and measure this distance. And I'm going to come up here to this vertex and measure that same distance. So now, if I connect these 2 points where they have this intersection, which I think I will label D, and point C, now I've got a rectangle. And in fact, if you look at this large rectangle, what I have here is a golden rectangle. So this longer side from A to C has a distance that is phi times as long as the distance from A to B.